Right, so now I can just take my pen. So we have two ways by which we can, represent this stack. One is array representation and another one is the linked list representation. So this is what we call it as the way by which not only stack, even queue, it comes like that. List, of course, is list also. Generally, it is meant for linked list way of representing it, but we can also implement a linked list using arrays. Okay, so under stack we have two ways of representing. So we'll study what exactly a stack means. I think as per the poll, many people have already studied, so I can just speed up the process. That's why. And similarly, under queue, the normal queue, then we have the circular queue, priority queue, and their applications. And under lists, OK, we have singly linked list, circular singly linked list, doubly linked list. So I've just taken only few. You can also have circular doubly linked list and array representation, all that. So these are nothing but your fundamental data structure. So what is a stack? Stack is a linear data structure which is operating with the principle of last in, first out. That is, last inserted item will come as first. That means we can say that a set of objects are stacked and the insertion and deletion both will take place from one end only. That means it is not double-sided. All operations have to be done from one end only. Now, how do we take care of this insertion and deletion? So we need to have what is known as a stack pointer, or I call this as top. OK. And you can see here we have many objects which are stacked. So this is, these are the objects which are stacked. And you can see here two operations in order to insert or push an element into the stack, any new element. And you can also remove an element from the stack, which we call it as the pop. So these are the two fundamental operations of stack. One is push, where a new object is put into the stack, and pop is nothing but the existing object in the stack is removed from the stack. That means if it exists, because we also have some exceptions which need to be taken care, something like, overflow and underflow, which we'll see in the next few slides. So this is a real world example where we have a stack of books. So the books are stacked. Now, when I say that a book has to be removed from the stack, so the topmost one is normally taken out. It's not pulling in between. A better way of removing any object is this. So we don't allow any in between element or the object being removed from the stack. So how do we know which object has to be removed when I have so many objects? So somebody has to monitor or maintain this. Similarly for pushing, assume that I need to put a new object here. Now I should know where should I put this new object. We say top of the stack. So how do we know that which is the top? So this is a pointer. Top or SP, stack pointer, is basically a pointer which will tell us that, OK, this is the place. Similarly for removal, again, we use the stack pointer. So we use only one variable here called top or SP, stack pointer, in order to push or pop. So what is the meaning of push operation? It's putting a new data element. Pop is removing existing one. So we can just design what is known as an ADT, abstract data type. So what do you mean by abstract data type? It contains the data, what are the types of data which we are going to store in the container, and what are the operations. So the combination of this basic data and the operations pertaining to this data structure can very easily be incorporated and designed as a general structure, data structure called as ADT. Along with this, we can also incorporate certain methods called as the exceptions or error conditions. So basically ADT, any ADT consists of three components: the data, operations with the data, and the exceptions. Now we can conveniently make a general kind, that's why it's called abstract data type. How you are going to implement this is different. So abstract means it is hidden. The details are hidden. So I can implement using array. I can implement using a list. OK, using a list, or you can have some other kind of methodology to implement this ADT or stack. Right. So what we are going to see here is bisecting all these things and try to see how exactly we can, implement this from scratch. Later on, you can see nowadays, most of the languages like Python or etc., they will have this ADT, which is available as a method or a package. So you can import very easily in Python or any other language like C++, C#, all that, where you can just use these methods. OK, so push may be an operation which you don't need to actually define, it's hidden. Similarly, pop is another operation where you can easily use it. You don't need to write code for that. So that's what we call it as an abstract data type. So it stores arbitrary objects. So you don't need to actually specify in ADT what kind of objects you're. It could be any object. It could be a student object, it could be an employee object, it could be a simple integer element, or it could be names of some of items, anything for that matter, or web page links. Any object can be stored in this stack. So that's why we say it's an arbitrary object. So insertion and deletions happen in last in, first out basis. On the other hand, queue, if you see, it is first in, first out. So you already studied FIFO and LIFO. OK, so what are the operations? Push an object. Pop, you don't need any parameter because we are going to return the object from the stack. Now here it's a void function. This is not a void function because it normally removes an element and returns it to the column. But here the object being sent as a parameter will be pushed into the stack. So top of the stack, you can get it size, how many elements are there in the stack at any point of time. The exception which I told you, which may be useful. This is empty may be useful just to check whether the stack is empty or not, or whether the stack is full or not. You can have is full also. So like this set of methods which are defined for stack operations and the data being stored and the operations put together, we can call it as an ADT. Now let's understand how the stack works. So this is a walkthrough of the working of a stack, assuming that we use an array to store our stack elements. Later in the linked list, we can think of how elements are stored in a linked list and achieve this stack. So assume that we have declared an array, because array means it's a fixed number of locations. So 5 is the size. That means you cannot add beyond 5. So generally, as I said, there is a pointer, stack pointer, which is going to track this insertion and deletion or push and pop. So we can initialize the stack to -1. Why we should do -1? You can just drop in the message box. OK, now a push operation, because this we are talking about the push up. So this push operation, before we push it, we have to increment this top because it's -1. And we know that our array, supposing C array or any array, starts from 0. So the moment I increment, it becomes 0, and hence I can push an element. So I'm trying to push element value that is 10. So elements are actually pushed based upon what top has. I mean, what is the address? So address is 0, and hence I can push this. So it is something like top of, sorry, assuming that this is S is the name of the array. So S of top, something like that. That means pointed by top, I push in my element called 10. That's it. After incrementing top. So top is -1, increment top, then I can push this element. Now assume that next 20 has to be pushed. So again, increment top. So from 0, it becomes 1. You can see here. And now I'm trying to keep my 20 here. And remember, top always points to a filled element. We can also design stack where top may point to an unfilled element. So keep this as an exercise. You can try to redesign or rewrite the algorithm, which we'll show later, in a way where top actually points to an unfilled location. OK, so next 30, same thing, increment top and etc. etc. Now after this, because now stack is full, after this, if you try to increment, we should not allow any element to be pushed. So we have to check this, what is known as overflow condition. Before we do that, we will also talk about pop operation. So imagine a scenario where we have currently 3 elements being pointed by top. So this is the one. So when I call top method, it will actually return this because pointed by top. So I can say that what element I would get out of this is pointed by top. So S of top, get the element and then put it in the local variable called E, and you can say return. Now before returning, of course, you have to do one more work because we are using array. Top should not point to this, which has already been removed. See, removing is not like erasing. OK, removing is just getting the element and then saving this or storing this in a local variable and then returning it. And the next time when I pop, my top should not point to this. It should actually point to this element. So I should actually decrement. See, from here, it should come down. So I should make -1. So from 2, it should become 1. So that's what it's done here. So I should actually make sure that my top becomes top -1. So that current value of top is pointing to a legitimate filled element in the stack. And similarly, one more pop will actually make top to point to 10, and one more pop will make top to -1, and now you can see stack is empty. And when I call pop at this point of time, it should say that the stack is empty, which means it's underflow. So that situation also should be taken care. So there are two important situations which should be taken care here. One is overflow and another one is underflow. So that's the situation which is shown here in this slide, where top is pointing to the topmost one where we don't have space beyond this. So any push operation being called with this, it should tell me an error. OK, so that's called as top overflow. We'll see how to do this. Supposing if I say max is my maximum, which is 5. So this is the size of the stack. So top -1 when it's equal to when top equal to max -1, which means that it's already full. OK, because the array starts from 0. So we have to have -1. So when top is equal to max -1, which is 4, it indicates that the stack is full. And similarly, underflow, when the top is pointing to -1, we know that stack is empty and it is not I mean, it's not feasible to retrieve or pop any element. So we say that it is an underflow. Let me just check whether we are recording. Yeah, it's being recorded. Thank you. So this is called as the underflow. So quickly going into the algorithm, as I already told you, stack is the array, maximum number of elements, that is n, top pointer and element to be pushed. So we'll assume that stack is an array starting from 0 to n-1. So if top equal to n-1, that is maximum -1, we say that it is overflow. We don't do pushing. Otherwise, we can actually increment and then push the element. Similarly, for pop, we don't need E, of course, because we're not pushing anything. So S, N, and top. So if top equal to -1, we say that it's an underflow, correct? Because stack is empty. And otherwise, stack has some elements so that you can save that in the temporary, that is pointed by top, put it in temp and decrement top and return temp to the column because it returns an object. So which means that you have popped the element. OK, so these are the two major operations like push and pop for which the algorithms are shown. You can code now in any language you like. That's why we say ADT, right? We can also replace this with is full, is empty with a simple functions or methods so that you can simply say if stack is full or is full and write stack overflow, or that means you cannot do any push operation. Similarly, check whether it's empty. So that checking can be implemented using two different functions. Now, one small drawback in this pop is a small issue. That's all. It's not a big one, but small. See, when I say return -1, -1 may be also a valid elemental value. OK, so how do we know that the returned value, supposing if I have an element -1 being stored in the stack, so how do you differentiate between the underflow condition and the real element from stack being popped? Right? See, because this is also an integer, a signed number. This is also an integer, which is a signed number. Right? So we have to differentiate between these two. Right? We have to differentiate. Otherwise, we will not know whether we are really popping or underflow condition we are detecting. So we have to slightly modify the logic in the coding. OK, as far as the algorithm is concerned, it's OK. But otherwise, or you can simply say return error code 401, something like that. We see in web kind of thing, But here, as a simple algorithm or coding, we have to take care of this difference. So how do we do that? Is defined here with void pointers. Now, I hope that all of you have knowledge in C, the fundamental programming language, and you would have also studied about void pointers. OK, so void pointer has a very important application in getting into what is known as generic value for the -1 or whatever it is. So what we have here is a special character. As I said, when an error condition occurs in web, you have the 401 error code. So something like that, I call here the error code as character C, which is like U or anything you can have, single character. So when top is -1, I can get the address of this, because it's a void pointer. So it has to be, because temp is a void pointer, so it has to be an address because the both left hand side and the right hand side should be of the same data type. So temp is a void pointer. This is also address. So void pointer advantage is that it can take, it's more generic, no? It can take any data type during runtime. Okay, that's the idea. So it takes this character value and returns this. So it really indicates that it's an underflow. On the other hand, it is getting the address of this items. Items is nothing but the stack contents, and top is declared as star pointer because top is going to be modified. Since it's modified, it has to be a reference pointer. Reference pointers are normally represented as star in C language. You can recall all this. Um, and as usual, decrement and then do it. So here, when I get U, capital U, I know that it is an underflow, right? So the temp variable is actually acting with dual role here, both for, because it's a void pointer, it can take dual role. Okay. So you can see here item contents is nothing but of the type integer. But here it's acting as character, no problem. Why? Because it's a void pointer. So that's how we can easily distinguish between a returned value and a normal stack contents. Similarly, for pop, you have, main program, you have to have this way in order to find out. So this is whenever you use a void pointer, you have to cast it. Typecasting has to be done. See, these are very fundamental details. I think anybody who has worked on pointers in C would know. Similarly, when you want to really display integer related one, you have to cast it because this is a void point. P is a void point. Because at runtime, it can take either character type or integer type. That's all the meaning of this entire exercise. OK, so normally in your exam, with my experience, they give these kinds of questions. Like they may ask you the stack contents after several operations like this. OK, so what is the stack contents after executing this statement? So push 5. So this current stack has only one element, which is 5. Next, push 3. So assume that this is the top of the stack, right hand side is the top of the stack. So 3 at the top. Now what is the length of the stack? 2 elements. Okay, return value is 2. No element will be affected in the stack. Pop, topmost one is 3, so that's popped, and the stack return value is 3, and affected stack is affected because it will not have 3. Is empty, true or false? It's not empty, so it is false. Similarly, pop, so 5 is gone, stack is empty, and return value is 5. Is empty, true. So like this, when you have a set of operations being given in the exam, and you may have to show what is the return value and the stack contents as your answer. OK, before we go for this applications, now any doubts? And we can check the poll results. Only 26 responses. Okay, thank you. So now we'll move on to stack applications where something to do with expressions, infix, postfix, and all that. So what we have here is infix, prefix, and postfix notations. We all know about what is infix. That is, operator is in between operands. Prefix is before the operands. The operator is before the. So here it's in between. Here it is post. That means after the operands. For example, this is an infix expression 2 plus 3, something like that. So postfix, it can be a very complicated expression also. And prefix, yeah, so the operator will be in front of the operands. Okay, so this is true even for very complex expressions, etc. So infix to suffix conversions, we can easily do it if you follow this simple step-by-step method. That means, for example, brackets have the highest precedence, parenthesis. So first evaluate that. So what is the postfix for this? AB plus. Similarly, CD minus. So you can see here, there's a shaded one, right? This is the operands. So now we can say this is nothing but AB plus star CD minus and then dollar, then E star F. We have to do the evaluation. So now what you do, star left to right. So these two could be evaluated. And sorry, this one has got a next precedence. So that also is now done. In the next step, now we have two stars left. So this is the first operand, this is the second operand. So AB plus CD minus E dollar star. OK, that is one. And star F. So now we have first operand is this, second operand is this. So this followed by this, then final star. So AB plus CD minus E dollar star up to this, then F, then star. So this is the final postfix expression of this infix expression. So why are we talking about this? We'll see soon. So stack actually is helpful in converting an infix to postfix. Now, why should we do this? Very simple. Infix expression evaluation actually takes time. In the normal method, it has to have repeated scanning, right? Supposing if you consider this expression, right? Now we have, we may have the highest precedent at the end, right? We don't know. Simple one is like A plus B star C. See, you can't do A plus B first. No brackets here. You can't do A plus B first. You have to actually do this first. Evaluate B star C because star has got higher precedent than plus. So what do we do? How do we know that star appears here? Because when you go from left to right, you will encounter this as an operator. So you can't do A plus B first. And my expression may be so big, I may have this star or division towards the end. There's so many terms. So unless I go through the entire expression once, I will not know. Again, I have to go through. Again, I have to go through. So like this, repeated scanning is required. But in postfix, it's not required. One scan is more than sufficient. So in order to do that, we actually use postfix expression. So this algorithm actually does, assuming that we have already a postfix expression, how do we evaluate? So supposing if I have a postfix expression like, as I told you, A plus B star C So the equivalent postfix of this is like this one is evaluated first. So BC star and A plus. So we have first operand A, second operand is BC star. So first operand A, then BC star. Two operands are n, then plus. So now what happens? I can scan through this expression postfix just once and I'll be able to evaluate how. For example, I keep scanning through this or browsing through this expression until I get a operator. So the moment I get an operator pop through. So while going from here, what I do is I will stack these operands in the stack. So for instance, I have A encountered first, push it. Next I have encountered B, push it. Next I have encountered C, push it. So my top actually points here, correct? So the moment I get star, I pop twice. So C and B. So top is pointing to this. Now these two operands, now I can perform this operation that is BC star. So this is done and push it back. So my stack now consists of BC star. This is the new contents. So now I have two operands in the stack. One is BC star and another one is A. Now again, go through the expression, which is plus now. Because it's an operator, I had to push again twice from the stack. So the first operand BC star, the second operand is A. So I know what is the value of this, assuming there's some value for B and C. I know what is the value of A, so I can easily evaluate this plus and push it back into the stack so that finally one pop will give me the final result. So that's exactly what this algorithm does. So top is initialized for stack. Position is to scan through the expression. As long as it has not reached the end of the expression, keep getting. So this is my first character. If it belongs to one of this, so I assume that these are real values, not A, B, C, D kind of thing. So push. So if C belongs to a character, which is a set of anything 0 to 9, then push it. Otherwise, pop twice. It could be plus, it could be minus, it could be anything. So you know what is the operator, and twice if you pop, you'll get two operands, and to perform this operation plus, minus, slash, anything, you get a result, push it back into the stack as I demonstrated already. Then increment the pointer until you get n, that is until you reach the end of the expression. Then one pop, final pop will get you the result that you can return. So postfix expressions do not require any repeated scanning. It just requires one scan. So the same thing what I've told you in terms of the values, it is explained here. OK, now how do we, because in real world scenarios, we don't write postfix, we don't write in prefix, we write only infix expressions. Why? Unmute, yes. I think it should be possible. But all people unmuting. I don't know whether it is possible. Now, globally, it may not allow mic for attendees. Okay. Hope that this. Are you able to? Yeah, Matru Prasad Mishra.
Hello, sir.
Yeah. Now you are able to unmute yourself.
Yes, sir. Thank you, sir. So
Okay.
I haven't
Yeah.
out of that slide. Can you go there?
Slide you want. Okay. Yeah.
Uh,
Which
the
one?
previous, the previous one, yeah. You are giving example like uh in fixed to post fixed part. So how you are sliding the
This
how you
one.
are sliding, yeah, how you are sliding the precedence wise.
You're talking about this, no?
Yes, yes, sir. Yes, sir. Like you write down the A plus B to the A B.
Okay. See, as per our knowledge, we
Okay.
know which operator has got the highest precedent.
Yes,
Correct?
sir. Yes, sir.
So based upon that, it's going to be evaluated. So for example, parenthesis has got the highest precedence. Okay.
Yes, sir.
So this one and this one have to be evaluated first, irrespective of any other operator.
Yeah.
So this is the precedence is going to be incorporated in our algorithm, as we'll see soon. Okay.
Okay.
So in order to make sure that your conversion is correct, what I'm trying to say is that you should follow step by step and not write at a stretch. So this way, if you do, you don't make any mistakes. Okay. So the first step is to pick the highest precedence and then convert that into postfix. For example, AB plus CD minus. So it's cool. So this is my operator. Say for example, X, this may be Y,
Yes, sir.
correct?
Yes,
So
sir.
now I have X, Y, E and F, only 4 operands. Similarly, next highest precision is dollar, is exponential. So I just evaluate this. So now I have X, maybe Y and Z. So only 3 operands. So now since we have both same precedence, so go left to right. That's the order of evaluation in any compiler. So what we do is X, Y star. Correct? What is X? AB plus. What is Y? CD, etc. Now star comes here. Sorry, star comes here. Then we have star F. So this whole thing now is this whole thing is my X. This is my Y. So X star Y is nothing but XY star. So that's what is written. So it's very simple to write your infix to postfix by going through step-by-step evaluation.
And
Yeah.
similarly, you're doing the conversion part also, like postfix to infix. Yeah. In example one, here it is like
Yes.
AB put
Yes. 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 Correct. Step by step. Because postfix means what?
six.
See, the biggest advantage of postfix is the precedence of the operators are already arranged in an
Yes.
order. That's why you're able to evaluate at one go. So when I say this is a postfix expression, assuming that it's a valid postfix expression, my first precedence is this plus. So AB plus is actually to be converted first to infix plus AB. Sorry, not infix. Okay, AB, A plus B.
Yeah.
Okay, A plus B. Now A plus B, C minus. So now I have two operands, A plus B, C, and an operator. So what is the infix for this? A plus B minus C.
Yes. Yes, sir.
So go step by step. So the advantage of postfix expression is this. Okay. Any other doubts?
No, sir. Fine. Thank
Okay.
you, sir.
Okay. So now we don't write postfix expression normally. We write only infix. Postfix is good for compilers to evaluate fast without any repeated scanning, but not good for humans. So we have not been taught in schools to write postfix, correct? We have been taught only infix. Our mathematics teacher has taught only infix. So we are very good at writing the infix expressions. So we have to make a compromise between the machine and the man. So I write in infix, you do whatever you want. And then, so what we do, we have a conversion algorithm here, which will convert infix to postfix, give it to the machine so that it can evaluate fast. So that's exactly what we call it as infix to postfix conversion with a stack. So stack plays an important role because we can store rather the details of these order of precedence inside the stack. Okay. So this I leave it to you. Many of you would have already done it. So I've given some examples also you can go through. And remember, this is a modified algorithm, a very powerful algorithm where it doesn't store too much in the stack. So there's some space complexity issues have been taken care, and it works for with and without parentheses as well. And what are the other advantages or applications of stack? Yes, you have maze problem, something like Harry Potter. I think most of you would have seen. So this is maze where the rat, for instance, enters here and it has to exit here. And the black ones are called as the walls. So you have to identify the route or the path for which, for example, if it takes something like this, then it will end up with dead end. Or it can again go like this, like this, like this, like this, like this, like this, like this. Yes, we have got a route. There may be other routes. OK. So we have to find out the route for that rat to come out of this maze. So once maybe, so I can just model this as an array. So this is an application of the data structure array and also stack. So 1 means it's a wall, 0 means it can go. That means it's open. So wherever 0 is there. So we have actually, we'll see later, this works on the basis of backtracking or not backtracking. Yeah, backtracking algorithmic method as well. So that, you can find out easily the path. And the return paths are actually stored in a stack. So the reason why stack is important is that supposing you just go, to some select some path and go and get it into your dead end, you should remember and go back to the previous one and then do it. So how do we remember? So whenever you want to remember and go back to immediate previous ones, you go for a stack. Okay. For example, in compilers, you have a function which in turn calls another function. That function in turn calls another function. So execution of this current function, it should go back to the immediately previous one. So the return addresses are actually stored in a stack. So that's how the compilers are designed. So how the solution is done, that's what it's explained here. Because the movement of the rat can be in 8 directions, right? North, south, west, east, northwest, northeast, southeast, and southwest. So you have to take care of all these functions. And if it ends up with some dead end kind of thing, it can take it from the stack. How we can, again, you can recall the Squid Game in Netflix, the strategies, you know. I think there is one game in season 3 where people can kill. There are two teams which are formed. One they can chase, another one they can kill. they'll be given a knife, etc. Anybody who has seen season 3?
Yes, sir.
Huh? No. Okay.
No, sir.
Okay. So just watch it. There's one game for this, and there is a maze kind of thing. So you will have keys. So you have to open it. If you open, the door will open and you can go. But otherwise, it is really a maze. This same thing. Okay, now let's move on to queues. Queue is first in, first out. So FIFO kind of thing. So we have normal queue, circular queue, and priority queue. So unlike stack, this operates on two ends, like one rear insertion and front deletion. Because people who come newly should stand next. That means not in the front. So that would spoil the queue discipline. Okay, so something like this. These are the examples where people, so this is a rear insertion. Assume that this is front. This is rear. So any new person coming should stand here. So that is rear insertion. So this is front deletion. So who has come first should be deleted. So first in, first out. So this is being used in many real world examples. Okay, so we need two pointers, unlike stack where it is everything is done at one end, but here it is two ends. So we need two pointers. One is called as rear pointer and another is front pointer. So we can initialize this. This is not the only way to initialize. As I said, for stack pointer being initialized to -1, you can initialize to 0 also, and you can redesign your algorithm. Similarly, here there are many ways by which you can, initialize, but this is most easiest way. Okay, so front pointer is initialized to 0, rear is -1, something similar to stack. And initially queue is empty, so I want to insert a new element 10. So what should I do? I should increment because I'm inserting. So rear pointer in increment R. So you get R, it becomes 0. So put 10 and keep going 20. That is 1, 30 at 2, 40 at 3. So similarly, queue has got limitations. That means the number of locations which you have already declared. So once rear pointer reaches the end, that means max -1, then it's a queue overflow. EQ operation or delete queue operation is nothing but based upon front pointer. Okay, so assume there are 3 elements currently in the queue. So front pointer is still pointing to the first location because nothing has been removed. So whenever you remove based upon front pointer and increment. It's not decrement, increment, because it should point to the next element which has been inserted. See why I have taken 10, 20, 30 because higher the number that has come late. OK, 1 means it has come first. OK, so now F has incremented, it points to this second person who has come, that is 20. So one more removal. So F will catch R. So when F is equal to R, when F catches R, what does it mean? There is only one element in the queue. So that's exactly what it happens. So you can reset the, so this is -1. You can reset the queue because you know that very easily no more elements are there. So what is overflow? When R reaches max -1. So that's similar to stack. What is underflow? When R is -1 and F is 0, that means no elements are there, right? Which otherwise F greater than R. So enter queue, same thing, n-1, it's overflow, something similar to top equals n-1. Otherwise increment R and insert. So you can see this exactly same as stack. Push, sorry. This is exactly same as push. So instead of R, if you replace this with top, it's done. Right. So when you come to DQ, it's not same as pop. So when F is greater than R, that means you can see here F is greater than R. See, actually, F will not cross over R at any point of time. which means f cannot be greater than r under any circumstances. F will follow r. When f reaches r, it's reset. So that's the beauty of this initialization. Okay, so if when this condition is false, that means there are elements in the queue. So you can easily get or remove the element pointed by f and store it in a temporary variable, and this is resetting. So if f catches r, you can reset the values of f and r. Otherwise, increment. That means still elements are there. F and r are not close. Hope that this is clear. Similar to stack, again, same questions, may be asked. Enter queue. So 5, next 3. So this is front. This is rear. OK, F and R. That's it. So E is empty, delete. So delete queue, for example, 5 should be deleted. So people should not make mistake. OK, there are some tricky kind of thing which may be asked in interviews and other places, exams, quiz, so many things. Write an algorithm to implement a stack using 2 queues. So I'll leave it to you. I have the solution given here. You can try this. Of course, nowadays, you just put this in ChatGPT, you will get a solution, but you can't always depend on ChatGPT because I have many examples myself that whatever it gives, yes, it can be an assistant, it cannot replace. So you have to make a lot of modifications, maybe required for your environment, for your machine, your operating system, your tool, etc. So you cannot 100% copy and paste your program and thinking that it would work. Similarly, the other exercise is implementing a queue using 2 stacks. So implement a stack with 2 queues and implement a queue with 2 stacks. The problem with the normal queue, I think I have that here itself. Yeah. Is that a situation something like, yeah, here. See, when you delete one more or remove one more element, F comes here. Sorry, F comes here. Or even with this situation. Okay, why that? Even with this situation, assume that I want to insert a new element. But I can't because R is already max minus 1. So max is 4, minus 1 is 3. So it's overflow. Actually, it is not overflow. You have an empty location too. So you are not able to utilize the locations or the array cells which are available to you. Right? It's available, but still unable to use it. So if I consider this as circular, that means making R back to this, then probably I can easily use this also. So make R to flow, not as a flat one, right? Make it as something like our world or globe is actually circular, not flat. Means you start at this point, then you'll get a dead end. No, you can travel back. Similarly, here in circular queue, you can actually travel back or reset it back to the front. So you can consider this queue is in a circular form. You can see here 0, 1, 2, 3, 4, 5, n minus 1, n. So 0 and n, that's what I showed you here. This is n. 0 and n is connected. I mean, in terms of the addresses. So if we can achieve that, probably we can loop around and then get our empty locations detected. So for which we need a simple formula with mod. See, mod gets you the reminder. So I can actually circular through. Okay, when my size is given as the denominator. So whenever you want to insert, don't simply insert based upon R value, but compute the R value with this R equal to R plus 1 mod n. And you whatever the address you get pointed by this R, you can insert. Right. And similarly for pop, Again, use the same, f r plus 1 mod n. So that will give you an address where the element is available. So that's exactly what it is explained here, that starting from initial condition, in this case, f and r point to 0. And if you want to insert a new element 10, then r equal to r plus 1 mod n. So here 8, right? So that is the maximum. R equal to r plus 1 mod n, right? So what is r value? It is 0. 0 plus 1 is 1. 1 mod 8 is 1 only. So it will insert at 1. You can see here. See, this will change only when it wraps around, right? Supposing assume that r comes to 7. So 7 plus 1 is 8. And 8 mod 8 is actually 0. So you are able to make r back to 0 by using this formula. That is the design of this formula. So this is deletion, same thing. And we can actually incorporate, instead of r equal to r plus 1, we simply use this formula. Similarly for f, we don't use the earlier normal queue, but it is plus 1. Priority queue, on the other hand, is insertion is not done based upon first in, first out, but it is based on the priority being assigned. So when we say a priority, elemental value and the priority. So this is a bundle based upon which my element will get a position, so that while retrieving based upon the priority, it is not first come, first served, but priority. For example, VVIP may get higher priority compared to ordinary persons, right? So something like that. Senior citizens may get higher priority compared to non-senior citizens. So there is some kind of priority which is attached. But how do we actually implement this? So there are two types of priority queues. One is ascending and another one is descending. Or minimum priority or min priority queue and max. So it's very simple that we use simply an index which is initialized to -1, similar to top equal to -1. And first element, so it is all based upon this 10 increment and then insert. Second 25 increment, and so index has come to the end. That's okay because it's full now. Now we have to worry about the retrieval, removal. Now we will assume that the highest elemental value has the priority. See here, I am not using two component, an extra component or extra value for priority. But here the elemental value itself tells me that higher the value, larger the priority, which means that when I want to remove, 25 should come out. So how do I make sure that 25? So first what I do, I'll have to find the largest element from this. So it's of the order of n algorithm. So it's very simple. So first I calculate or compute or find out which is the largest one. I know its position. So what I do, I just return that because that is the highest priority. That fellow is served. And in order to make sure that I don't put any empty pockets in the array, because it should be a compact array or a contiguous array. So what I do, last element, I'll just save it here or push it here. So 21 will be pushed here at this place. So you can see here, because I'm not bothered about where my elements are stored in the array, because I'm going to find the highest value and then get it. So next time when I want to retrieve or remove, I again execute my max finding algorithm So that fellow will find this. So this is the highest next priority. Next, last one will be saved here and index will come, will be reduced, of course, decremented. So index points to this because when a new element comes, I have to actually insert that. So both insertion and deletion should work. So next again, find the largest value 17. Done. So it keeps going. So priority queue in an array can be implemented using this where my complexity becomes of the order of n. So simple. So the corresponding algorithm is given here. So this portion actually will find the maximum elemental position, and this will actually swap the last element with the current max position, and index is decremented to make sure that one element has already been removed. Insertion is very simple. So deletion, you have to do this much of work. Okay, coming to lists, linked list again, most of you have studied. And we have plenty of types here. Singly linked list. How do we implement stack? How do you implement a queue? Ordered list. Then circular list, doubly linked list, circular doubly linked list. So there is a big list. You can go through my book. You will get complete details, code in C, I think, yeah, etc. So what is a list? List is nothing but collection of nodes, each node consisting of data field and the next field. And this is mainly for the runtime kind of storage. It's not like array where you don't have any fixed number of locations. You can keep going, no problem. And you should be able to create a linked list. So linked list, you have this data field compartment and the next field. Since it is stored in memory, not as a contiguous kind of locations like arrays, so you need a next pointer. So this node 1 actually stored at some address, say 1000. Node 2 may not be stored exactly next to it. It could be stored at some other random location, let's say 2000. The third node may be stored at some other location. So you need, it's just like a chain, So the links are very chain, could be normal chain being used for dogs, chain being used for straps in watches. They're all attached, which means that this field has got 2000. That means next node's address. OK, so that's exactly what we call it as node. Suppose if you want to add new node, it is possible. You can just request for a dynamic allocation and then you can add nodes. You can delete, you can relink. Adjust. So you don't need to actually worry about deletion also. You just want to delete this. Just store 3000 here. That fellow will point here. That's it. So this you can remove the memory for this. So there are a lot of advantages that dynamically you can request for memory. So the exact number of memory which is required or the size required can easily be allocated because that's what the compilers do. Array, when you declare, it is contiguous. Address calculation becomes fast and it's faster retrieval. Dynamic allocation, on the other hand, has advantage that you can get the memory, right amount of memory, no wastage, etc. In arrays, wastage of memory, for example, I allocate 1000 int A in C, I may use only 50. So remaining 950 is wasted that way. So this comes under self-referential structure. You would have studied in C language that this is the self-referential because before the completion of the definition of the structure list, actually it uses this definition. Usage of this. So such kind of declarations, we call it as self-referential. So ADT for list, again, we have the sequence of objects being stored in the nodes, and we have size is empty, all that. You can also get insert before, insert after, insert in between, because now that it's a list. Python, I think those who have already studied, list is quite commonly used there, and removal also. Remove the first node, last node, middle node, all that. Okay, applications, I'll leave it to you. You can go through my other PPT also. Very simple walkthrough of the insert front. Assume that there are 3 elements already in the linked list pointed by P, because there's one pointer which is required, which is sufficient because the rest of the nodes are all linked. So you don't need individual pointers. Even if I have 1000 nodes, no problem, one pointer is enough. Something like a train where one engine is enough, okay, to pull all the bogies because all the bogies are connected. Okay, now create a new node which is going to be inserted at the front of this 15. And so this new node has a data 99. And my advice to you, if you want to master in this linked list, first write the figure and then write the code or algorithmic statement. So I have created a new node and inserted the info field of that queue, which is this. Then I have to link it. That means this, I have to link it to this. So what is this? Is next of queue. So you can see here. So next of queue should take a new value, which is nothing but P, so that this queue will point to P. So that's exactly what is shown here. So next of queue should take the value of P. That means this should be modified. So whatever is being modified should appear on the left. Okay. Then P is no longer should point to 15 because the new node. So this should actually be moved to this, correct? So P should take the address of Q. So that's what it's come. So now P 99 points to 50. So there are only 2 instructions required. One, this pointer, because don't alter this, don't change this order. It's very important. See, otherwise you will lose the link. See, that's why people are afraid of writing linked list based programs, because you will get memory fault core dump when you open Linux kind of environment. And it's a fatal error. Why? Because when you wrongly assign this, because it's a runtime memory allocation, sometimes this address might point to some operating system area, and obviously it gets irritated. So it throws an error, memory fault core dump. Okay. So in linked list or while working with linked list, you have to be very careful on the addresses which you are using, especially linking. So the algorithm is same, like get node as a new node, put the new element, etc. Same statements I have put it here, what I've shown. So this can be written provided if you have the figure. So write the figure and then write this code. It's very easy, our algorithm. Same way you can insert middle, you can insert at the end, and you can delete, etc. So I'll leave it to you to go through this because you would have already written programs, Java, C, whatever it is, and should be able to. And similarly, doubly linked list, instead of one link, you have a link on either side. That means the left link and the right link. Why? Because you can go through or walk through either way. In singly linked list, you can walk through from left to right. That's it, dead end. But here it's two-way. People can move from here to here, here to here. So you can keep going. Circular doubly linked list, Netflix. So you can keep going left to right and right to left. And also it wraps around, So that's the advantage. But writing code and deletion at the middle with the doubly linked list again is a bit tricky. You have to follow the sequence. If you don't, then you will end up with again errors. Okay, so this is the order of execution 1, 2, 3, 4. So if you do that, you can easily link it. So write the figure and then write the code. One caution is that don't delink. First link and then delink.